to episode 5 of Q for Problems. Today I'll be looking at problem 5 from the Project Euler problem set, and it wants us to find the smallest positive number that is evenly divisible by all the numbers from 1 to 20. So let's have a look at the solution. So to start off, we can use the example given, which was that 2520 was evenly divisible by all the numbers 1 to 10. So we'll use that to build up our solution and then extend it to 20. So we can create all the multiples of 10 up until 2520 by writing 10 plus 10 times till 252. That gives us all our multiples of 10. And then we want to check, are these divisible by the numbers 2? We don't need to check 1 because everything's divisible by 1, but then we check 2 until 10. So we've seen this in previous episodes. To check if something is divisible, we just use mod, which will return a 0 remainder if it's evenly divisible, and if it's not 0, then it's not evenly divisible. So we just check where x mod of each of the numbers in the right argument, which is the numbers 2 till 10, as you can see. So if I run this, you can see that this first row will correspond to all these numbers in x divided by 2. Then the second one, or sorry, not divided by modulus of 2. And then the second row will be with modulus 3, and so on. So you can see that 2, 5, and 10 will always be true because we built this list from the multiples of 10. So we don't really actually need to check these. We can essentially get rid of them because we already know that they are divisible. So to do that, we can instead construct on the right hand side here. So if I delete this right hand side, we can say something like 3 plus till 8. Just going to run this just to show what that produces. So you can see that's got rid of 2. We can get rid of 5 and 10 as well by doing except 5, 10. So when we run this again, now we're only getting for those relevant values. So what we actually need to do now is check that a full column has to be true, as in it can be divided by, that number can be divided by all the numbers from 3 till 9 and excluding 5. So to do that, we can just say min on what we just had before. If I just copy that down, x. If I run that, you can see that collapses in a single list, which means it's the minimum of each column. So if there's a 0 at all in each column, it will return 0. Otherwise, if the full column is 1s, it will return a 1 in these positions. And we know that from the example or the question that 2520 is that first number, so it'll be the very last item in this list. But this is just to see. So all we need to do now is index into x, the original x. So we just do n or x. Got my insert on. We just do x where and run that, and as you can see, it gives us the result. So we can extend this to 20. However, the problem is that we do not actually know how far we need to go up. Like here, I've generated a list of multiples of 10 up to 2520 because I knew that was the final point. But we don't know what 20 is going to go up to. So instead, we need to use a while form of the over accumulator to iterate until we find such a number. So to do that, let me just set my numbers that I want to check equal to n. So we'll just remove this old stuff. Numbers I want to check is equal to n. And then to actually do the iteration, what we need to do is we need on the left needs to be a predicate function that will return true or false based on some condition, and the loop will keep going, the iteration will keep going until it's false. We want to do 10 plus and then over 10. So this will just continuously add 10. Starting at 10, it will keep adding 10, i.e. building up this multiples list again until this condition is false. And what is the condition? Well, it will be any mod, and you want to do that with all the numbers in n. So this will do mod with each of these values. So over the iteration, it will continuously. So the first item is going to be 10. It will do mod of 10 with each of those numbers. And then any will return a true if there's any non-zero term. So if there's any non-zero term, that means that all the numbers were not divisible, which means that we want to continue the iteration. So this will return true, and it will be false at the stage where this mod 10 returns a list of zeros, in which case this NA will actually give a false value, which means that this predicate will return false. So the next thing to do then is to actually extend this to 20. So I'm just going to run the 10 on first, and you can see I've produced the right result. So to extend to 20, we need to change the values that we're looking at here. So we can do 3 until 17. And then just like we dropped on the ones that we don't need to check, we can drop the multiples of 20, which is going to be 4, 5, and 10. So if I run this, you can see that gives me everything. I don't need to check 20 either because we're generating a list of the multiples of 20. And then all I need to do is change these 10s to 20s and run. The previous solution was a simple idea, but it's actually quite slow. It can take a few seconds to run for 20. So instead we can use a popular method for calculating the least common multiple to derive a better solution. We can define a few mathematical properties of numbers to come to a definition of the least common multiple. So if a number a divides b evenly, that's because the prime factorization of a is contained within the prime factorization of b. So an example shown here is if 10 divides 100 because the prime factorization of 10 is 2 times 5 and the prime factorization of 100 is 2 times 2 times 5 times 5. So you can see that the 2 times 5 is contained within the prime factorization of 100. So that means we can arrive at the definition that the least common multiple of two numbers a and b is equal to the union of the prime factorization of both numbers. Unfortunately, however, we can't just use KDB's union function because, as shown here in this example of a equals 5 and b equals 20, the prime factorization of 5 is 5 and the prime factorization of 20 is 2, 2, 5. To do the union here, we need to keep hold of the highest order of each number, meaning that we actually, as you see there beside the desired, we actually want to keep the two twos because that's the highest order of twos that we've seen. And we only need the 1 5 because that's the highest order of 5 that we've seen. So if we were to then have another number and we've seen 3 2's, we would have to take the 3 2's rather than the 2 2's. So we'll have to define our own function to do this union. So to create this function, we can make use of the prime factorization functions that were described in episode 3. So if you haven't seen that episode, go check it out and you can see the function described there. But it can be actually found then in the math library if you check out the GitHub repo of this, which will be linked below. So we can do the prime factorization by calling our factorization function. So it's in the math library. It's called pfact. And we'll do that on each of the numbers 2 plus till 9. So again, we're going to do this, derive the solution for the example shown in the problem, and then we'll extend it to 20. So you can see this gives me the prime factorization of all the numbers. So what we need to do now is group this and only go over this list and keep the highest order of each number, each unique number. So first, to group, we can make a small edit here. And rather than just doing prime factorization on each, we can actually do a group on each as well. So run that, you can see now each of these rows has actually been turned into a dictionary. So this corresponds here to the position, the index, which doesn't really matter in our case of each of the numbers. What matters is how often the numbers appear. So when you can see here, there's multiple numbers. You can see 2 and 3. It's actually a list of lists. So if there's 2 indices in here, that would mean that it's actually 2 to the power of 2. So after grouping, then we can use the count to count each of the indexes and tell us the power. So once I run this, you can see here that this first one is 2 to the power of 1. The second is 3 to the power of 1. You can see now for this corresponds to the two twos. It's 2 to the power of 2. So after we've grouped, we can now use, we're going to have to go over this list and do this all at once, because we need to essentially keep the highest order seen so far. So the highest order 2 will be 2. And by the time we get here, it'll now have to be updated to be 2 to the power of 2. And then when it gets to this point, it'll have to be 2 to the power of 3. So we're going to iterate over this list to do this. So we can do this using the over or scan. So we're going to use the scan here. So what I'm going to do is, instead of this, I'm going to replace round brackets with braces, the parentheses with braces. I'm going to put the y here, so this will take 2 arguments. The first argument is going to be the dictionary of this grouping essentially so far. So at each point, it's going to be the most recent dictionary of the factors and their powers. So the dictionary, the key is the power, the key is the factors, and the values are the powers. So we're going to start off this dictionary, we have to start it with a single element dictionary, which contains essentially like a redundant value. Now, the reason we have to include this is because why we don't just have an empty dictionary here is because when we do this comparison to see, is the power greater than, whenever you compare with a empty dictionary, it will always return you an empty dictionary. So that can cause us problems. So we're going to start with this kind of redundant. This is just one. This is a null with a 0. So this isn't going to contribute to the final product of this. So it's okay to have this value in here. And then we'll have our 2 till 9. So this will make a bit more sense now when I run it. So if I run, you can see that this has just produced exactly what we had before. So we've got it now in an iterating form. However, we need to do the comparison now. That's the reason we've changed it into this form. So to demonstrate what we're going to add this, I'm just going to create a small example. So if we say that we had our current dictionary, right? So this is the first argument was, say, 2, 3, both were to the power of 1. So that's our current. Now let's say that on the next iteration, this is the next group that we're going to actually iterate over. So it's going to be 2 to the power of 2 and 5 to the power of 1. What we expect here is the 2, because it's now going to a higher power, 2 to 1. This should, the x should be updated to essentially contain 2 here. However, 5 hasn't been seen before, so it just can easily just be joined onto this list. So that's what we're trying to do on each iteration, is update the dictionary with any of the previously seen ones to see if it's a higher power, and if not, we can just simply join. So to compare, x greater than n. Sorry, I need to define these 2 items. So x greater than n, you see now it will return me a true value of the ones that we should add. So 3 doesn't need to be changed or doesn't need to be added. 2, it needs to be updated, and 5 needs to be added. So this is a Boolean value now in the value part of the dictionary. So now if we want to return the keys of that, we can just use the where keyword. So if we do where and then our comparison and run that, so you can see now this gives us the actual factors as symbols. And then we can index back into n to get the new updated dictionary. So if I say k is equal to that where part that we just seen, and then the k equals n. So where n, remember, is the new dictionary, and k now here is this the keys that we're concerned with. So if 2 wasn't a greater value, we would just drop the 2 here, but in this case it is, so we need to update the value. So I run this. You can see now this is giving me 2 to the power of 2 and 5 to the power of 1. And then we need to join on to what we originally had. So I just do x join. So any keys that match in x will be actually overwritten with the right hand side. So the 2 matches, so that will be overwritten with 2, but the 5 will just be joined on, and the 3 will be left untouched. So you can see now we've got the updated dictionary as the result. So if we put that all together in a function, I'll just paste this in. This would look like this. So if I run that to define P, so P is now this dictionary for the numbers up to 10. And then essentially to get the power now, we can just do the value. So the value here is the powers, and then the key is the actual numbers, the factors, the prime factors. So if I run value take each of those, each right or each both, sorry, of the key, we get then, you can see wherever there is a power, and you can see the first item just produce an empty list, which will just get destroyed now by arrays. So it just does not contribute at all. You can see 2 to the power of 3 gives us 3 2s, 3 to the power of 2 gives us 2 3s, etc. So we're going to do a product then over this list. So first we essentially raise it, and you'll see now that this empty list is gone. It's a flat list, and then we can just do the product of those values, and you can see we arrive at the answer. So that gives us our least common multiple function. So again, I'm just going to copy and paste this part in because it just looks at what we had before. So this is a function that will calculate the least common multiple of the least common multiple of a list of values. So the actual solution then will just be LCM on 2 plus till 19. And you can see that gives us our answer. So to test performance now, I've put solution 1 and solution 2 into a function to make them general so they can apply to any number. So I've just because of the time taken to run this, I've pre-run the performance test. So I've saved the values in this table T. So if I run that, so we can see when the input was 10 for S1, it took this amount of time. For 10, it was actually still a good bit quicker for S2. However, the real performance benefits can be seen here when we did it for the input of 20. You can see this took almost 10 seconds to run S1, whereas S2 was less than a second. So the actual benefits of using the prime factorization are quite evident from here. So that's everything for this problem on this episode. Thanks for watching, and make sure you leave your solutions or comments or ideas or whatever in the comments below. Thanks.